Okay, good morning, everyone. So today we will start to move on to the next topic, and the topic is mass transport induced failures. So in this topic, in this reliability issue, we mainly discuss the issues happen in the back end of line, especially related to the interconnection line. And this is very important for the recently that it's very well-known technology that we need to move from the planar integration to the vertical integration. And one of the way we can do the vertical integration is we are getting to use these 3D integrations. So far there are several different approach to the 3D integrations. The first one is TSV 3D IC integration. So in this case, we are actually considered to connect the different chip. We have the chip 1, chip 2, chip 3, and each one we will connect it from this, what we call the through silicon vias, TSVs. So basically, we use the through silicon vias to try to connect the chip in between, but in the vertical way. So that's what we call the TSV 3D IC technology. And on the other hand, we have also, this is something that is ongoing now for our vertical integration to have the better chip density, also the safe the chip area, also the interconnection line between each chip can be highly reduced, and that can improve the overall system performance. And also on the other hand, we have, of course, we have a different 3D IC approach. The first one is the TSV 3D IC, and second one is a face-to-face 3D IC. So that's mainly based on we have this bonding. So we have the two chip, and then we try to bonding these two chip directly. So we have this is a chip 1. So we have the chip 1 here. And once we finish the fabrication for chip 1 and chip 2, we try to turn around upside down for the one chip and use the bonding to connect with another chip. So that's we call the face-to-face bonding technology. And also we have the one that we call the monolithic 3D ICs. And also we have right now the main what we talk about the ABC is the future of a 3D IC. Some of them is already realized, some of them still under development. But I believe so far the mainstream so far in the technology is based on what we call the 2.5D IC. So in the case of 2.5D IC, we actually have what we call the interposer. So this is the interposer try to connect these two chips together. So based on this interposer, we can have the different chip all located in the interposer, and then the signal can be go through from chip 1 and chip 2 from this based on this interposer. So this is a general overview for the 3D integration technology. But overall, if you look at this 3D integration technology, for example, the TSV 3D IC, that's overall is our automotive goal to have this TSV, because that can give us a chance to vertically stacking the different chip and connect it by this TSV. But now you probably will see that we have so many these TSV. And the issue is that if you have the one signal going down from the top, you have go to this, go to all kind of the TSV vias. And the problem is that the current flow in this way is not directly in the straight line. It must have a certain current, what we call the flux divergence. So you will have it first to turn around and turn to here. So in this case, we start to see that they have the huge reliability challenge in the back end. That's generally what we call the back end reliability. And also the contact between each one might also suffering lots of reliability issues. And most of the reason is due to what we generally call the mass transport induced failures. So that's why we are in this topic, we will have to dedicate to talk about this. So if you try to look at another schematic, this is also the schematic for the monolithic 3D IC integration. So basically we can divide our technology with a different module. So sometimes in this case we call this as a front end. So front end is mainly related to our transistor. So we have a transistor here. This is our transistor. So in this transistor we have the gate, we have a source, we have a drain. So in the front end, we already discussed the front end reliability issues. That is already discussed in the last several weeks, including the BTI, including the TDDB. So that's mainly focused on the transistor level. And on top of the front end, we will start to have the, for example, now we call the middle end. And on the top of middle end, we have the back end here. So basically, we can divide our overall technology between the front end, middle end, and back end. And the middle end depends on how many chip you are staking on. But basically, we can generally divide as a front end and then the back end. And also, of course, in this schematic, the middle end is also considered as another transistor here. And now to connect with the transistor to transistor, we must have this vertical interconnection line with each other. So that's what we call as a TSV. That's what we call the TSV. So, and now if we look at the back end, we can find out that in the case of a back end, we have the back end is mainly constructive. The back end is mainly consider the group of the interconnection line in the last part of our chip to connect the signal to the outside. So that's generally we consider as a call as a back end. So inside the back end, actually there's no transistor. It's mainly a lot of interconnection line and lots of the passivation. So imagine you have the electron starting. You have a signal starting flow from here to here to here. So that's our electrical signal here. And we will have the output bias, for example, like the VDD1. And we have another bias like a VDD2 here. So this is a different VDD is going to provide the signal to our transistor to provide a bias to our transistor. But at the meantime, we will start to foresee because of your bias here, you have the electron will flow here. Your bias here, you have another electron will flow here. And these actually will start to create a certain reliability issues. And then the general reliability we can foresee here is, for example, we have two different VDD2, we have the VDD1. So the bias in between the VDD2 and VDD1 is definitely not the same. So we will have the voltage difference between these two. So we will have the VDD1 minus VDD2. As long as we have the voltage difference between the two metal insulator metal, and therefore we definitely will have the issue as a TDDB as well. If you consider this is a one metal, this is insulator, this is another metal, and for sure, if you look at the structure of this metal insulator metal, that's exactly fit what we have been discussed from last week about the TDDB. So TDDB is actually another very important issues in the back end as well, not only in the front end, not only in the gate dielectric, not only in the transistor, but also it's very crucial in the back end, because in here region, we actually try to provide the constant bias to activate our transistor, to provide a signal of transistor. And as long as we have a voltage difference between these two metal connection line, and therefore we always have the TDD issues in the back end as well. And also another issue is that in the beginning when we introduced this class, we already talked about that once you consider a bunch of interconnection line, but once your current is not flow in the always straight, there's a certain current, that's what we call the flux diversion. You have a certain current diversion. For example, you flow to here and will be divert to this region, and then you come back here. As long as you have this corner, you always create the issue that your current density cannot be uniform. And in that case, we will have the issue what we call the EM. This is a term what we call as electron migration, which we will be discussed in detail in this class. So that's also another very important issues here. Actually, not only in the back end we have the electron migration issues, but also in the front end we can also have an electron migration issue. As long as you remember, the electron migration is mainly happen. You have the carrier, you have electron transport from one place to another place, but unfortunately the material from one place to another place is not the same, or the current direction is not the same. We always have this electron migration issue, and that means actually in the front end in here, as you probably already you have been in this, although you might be the new to our the department, you are being new for the first year in master student, but you already probably know that when we try to fabricate a transistor, we have a silicon substrate, but if we want to make a good contact, we definitely have to use a different material. So if you look at this region, this is a contact between the metal and semiconductor. That means this is a current will flow between the two different materials. And as long as the current flow to the two different materials, we always have the electron migration issue. So in here, we also have the issue, what we call the contact electron migration. So that's a general overview that just for sure later we will discuss what exactly the reason cause to drive the electron migration, what is the main issue in the back end. But this is just let you know that the issue is getting more and more serious, because as long as you have the more complicated 3D integration, you have more chip stacking on top, you always face more serious issue with this interconnection line reliability. And also another issues already happen, no matter you are working in the 3D integration or not. In the general planar integration, always suffer another issue for the back-end reliability as well. This is because of one of our goal, you already know, one of our goal to make the advanced transistor is try to scale it. So we are mainly in the previous lecture, we mainly talk about the front end. So we mainly talk about we are going to scaling the dielectric. But in reality, we are not only scaling the dielectric, we're also scaling the channel length. We're scaling the overall pitch. But if we want to scaling overall pitch, and then the issue is we need to make our contact as smaller as possible. So once we need to scaling the pitch size, of course, not the channel length, not the gate to drain distance, but also our contact region need to decrease, especially the contact area. But what happens if our contact areas decrease? We still require our transistor to perform very high performance application. So that means we expect our transistor still need to be fixed with a certain current, output current, right? So output current should be fixed, cannot be reduced too much. But on the other hand, your contact area is reduced. So that means your current density is highly increased. But as long as your current density is highly increased, that's also creates another reliability issue. Because you can imagine, once your contact area decrease, so your current density goes through the contact is increased. But on the other hand, we also try to reduce the thickness of our interconnection line because we want to save the chip area. But the problem is, if you try to make your interconnection line thinner and thinner, and then your current density is also high. And the current density is a main driving factor for this interconnection line related reliability issues. Let's look at some of the examples. So, although this paper is published in the 2012, that's almost more than 10 years ago, but still nowadays, we still suffer a lot of the TSV interconnection reliability issues because of our expectation for our transistors getting higher. We want to higher current, we want higher performance, we are stacking more and more, and that always make our reliability getting issues. So first of all, this is an example of the electron migration in 3D IC TSV interconnects. So this is an example. So the general idea is that once you have the electron carrier flow from one side to this TSV here, and then we start to find out that after you stress for a certain time, you will see this is experimental result here. So you have experimental result. This is a resistance versus a time here. So you can find out the y-axis is our resistance. So that means we are trying to understand the interconnection resistance, especially at TSV versus the different stress hour. And then at the 300 Celsius degree, if we try to stress our interconnection line with 180 milliamp, after a certain moment, the resistance is suddenly increased. So that means our TSV got some problem. That's why the resistance increased huge. On the other hand, this is 270 Celsius degree stress at 100 milliamp. We also suffer the same issue, but just because lower current, lower temperature, so you need longer time. Start to see the increase of this resistance here. So this is because of mainly related to formation of the, for example, the voiding here. Why there will be the voiding formation inside the TSV certain region? This is back to the pretty fundamental understanding of our electron migration in the interconnection line. So as we already mentioned this in the first class, when we talk about the mass transport induced value, we are consider there's a piece of the interconnection line, and then we apply the bias here. So our electric field is in this direction. But now, actually, electric field is from left to right. So that means our electron is flow from the right to the left, right? And because of the electron, during the flow of the electron, create the huge momentum, and this momentum will exchange to, for example, in our case, we consider this is the copper line here. So this electron will start to push the copper atom toward the left. Start to push the copper atom toward the left. And at a certain moment, you can start to foresee original, we have the interconnection line like here. But now, there's a certain material will be pushed toward the left and will be accumulate in the left region. So after a certain moment, you will see there's some change for our interconnection line, because you are getting more and more coppers accumulated in this region. So that's generally we call the heel lock. So we'll have a heel lock formation on the one side, but of course, the overall amount of the copper concentration is the same along the interconnection line. So that means if you increase the copper at the one side, that means there must be somewhere the copper is depleted. So therefore, you will start to see the depletion of a copper on the another side, because all the copper atom has been pushed toward the left already. So this is what we call void formation, and this is the reason why our resistance is increased, because of your interconnection line is getting thinner and thinner, so your resistance is getting higher and higher. So that's why in this region we start to see the void formation. And you can see this is an experimental TN result here. So you can see there's a void formation here, and that's why this is our TSV flowing here. But now this region is getting thinner and thinner, and therefore resistance is getting higher as well. So that's caused a problem for our TSV interconnection. So this is one example of our the electron migration in 3D IC TSV interconnects. Okay, so that's a general overview to see that what actually the industry concern about this interconnection reliability. But now we will still go back to some fundamentals to understand why this atom will be moving and why in the end will cause reliability concern. So this atom movement, that's generally we call the mass transport. And this mass transport issues will lead to the atom movement in the solids here. So we will talk first to discuss why fundamental physics, what is a fundamental physics that can help us to understand. And second one is electron migration. And also the third one is electron migration is mainly talking about the interconnection line. But also we have been already know, actually you have as long as you have a different material interface, you always got the problem for electron migration. So that's also happened during the contact region. So that's why the third part is a contact electron migration. And last one is what we call the stress voltage. In here, the stress voltage is not the electrical stress. What we call the stress voltage is what we consider as a mechanical stress. So in the back end of line, we actually have lots of the metal and lots of passivation. So imagine you have the metal 1, you have the metal 2 here. So that's our M1 and N2. And of course, to try to isolate the signal between the metal 1 and metal 2, we definitely need to deposit a certain insulating material. So that's what we call the passivation. So this is the schematic that's similar to the case like here. So we have the metal, for example, in here we have the metal 1, we have the metal 2, and in between we definitely have this passivation. Try to isolate these two regions. And the problem that can cause the mechanical stress is related to what we call the coefficient of the thermal expansion. So what is the coefficient of thermal expansion? I think this is pretty like the very, when we are the very small key, we already know that if you have a different material has a different thermal expansion coefficient, that's related to the thermal. So once you put that in the certain high temperature environment, you will start to see your material will getting expanded. That's due to the coefficient of the thermal expansion. But now the problem is that we have a metal 2, we have a passivation, we have a metal 1. But each metal might use a different material, and each passivation also might have a different material. So different metal, different passivation might have a different thermal expansion coefficient. And also, when we try to process, if you imagine you try to process from bottom to the top, actually our semiconductor is being again to involve in the thermal process again. So usually the front end is the highest temperature. For example, probably the ohmic contact will be formed at 600 Celsius degree. But afterwards, once we go to the back end, we'll try to lower the temperature because we don't want the temperature to influence our front end characteristic. But still, there's some thermal treatment, probably around 200, 300 in the back end during your passivation, deposition, during your metal deposition. And this, again, the temperature treatment or temperature-related process will start to lead to this metal or passivation has a certain thermal expansion. So we have the many high temperature process. For example, our ohmic contact annealing. Our ohmic contact annealing is a temperature around 600 Celsius degree. And sometimes we have the passivation deposition. We try to lower the passivation deposition temperature, but that still involves a certain temperature. Probably in the range between 200 to 500, depends on what kind of the process you will use. But idea is we always want to have very low temperature in the back-end process because we don't want to influence our front-end characteristic. But as you see, the semiconductor, the whole chip is being again in a different temperature environment. So the material has a different thermal expansion. So the different thermal expansion definitely in the end will cause what we call the mechanical stress. So that's also one of another issue in the back end of line. This is because of this mechanical stress in the end will cause the voiding in our interconnection line. In the end, that will make our interconnection line has a huge resistance. Okay, so first let's start to go to the introduction to this failure mechanism. So what we discuss here is the failure mechanism are related to the mass transport, which is the physical movement of the atoms. And when we consider the driving force of the atom movement can be either due to thermodynamic non-equilibrium or some additional external forces. And lower operating temperature reduces the reaction to very slow level. So that's why one of the possibility to avoid this interconnection line related reliabilities, we want to lower the temperature because we can highly reduce this reaction rate. And mass transport induced failure can lead to the compound formation, interdiffusion, voiding, electron migration, stress voiding, and also the contact reaction. So you can see it's mainly related to the materials reaction. It's mainly related to the chemistry reaction between the two different materials. So that's why we have the compound formation, we have the diffusion, we have some of the reactions here. And typical IC contains 10 to 700 meters of the narrow thin-film interconnection line. So if you try to really count how long of our interconnection line in our product, actually the interconnection line inside our product is much longer than you expect. It's actually in the order of the several hundred meters of our interconnection line in our one product. And average interconnection line is around 100 micrometer. And if you try to consider the typical, like the data line, typical cable line that can be 1 or 2 centimeter long, and this will also cause the current density in the order of the 10 to 5 or 10 to 6 amp per centimeter square. Now we're back to the why there will be the alternate movements. So we have been already seen is in the beginning in one of our previous lecture to discuss how the alternate movements in the solid. So movement alternate diffusion in solid is generally governed by the energy barrier of the delta G here. And this is a case without driving force. But once we have the external force, then movement in the one direction is larger than another direction. So that's why we will have the movement from 1 to 2 is a lower barrier than the movement from 2 to 1. So this is because we have this applied electric field. And in the end, we can try to estimate the net rate of the alternate movement by consider the R12 minus R21. And based on this, in the end, we can also get the equation that we call the Nernst-Einstein equation to try to estimate the alternate velocity movement inside the material, which is our velocity V is correlated to our driving force F, and where D is a diffusion coefficient that's related to our D0. So D0 is related to our material property exponential minus ED, so that's activation energy, over KT. So that's a pretty like the basic equation that we try to understand the alternate movements. So now the previous one has been something already discussed in the previous lecture. So this will be not the main focus on this part. In this part, we are trying to understand how will be this equation in the end to help us to understand the electron migration. So basically, this Einstein equation describes the mass flux of the atom. So our current is equal to concentration times velocity. So we have a concentration is C here times the velocity, and the velocity is the equation we already derived in the previous slide, and then that will be equal to this one times force, and then force also will be equal to gradient mu. So the F is equal to chemical potential gradient mu, or the driving force. And this driving force can be caused by the three different factors. The first one is electric field. So that's the first. And the second is concentration gradient. And the last one is mechanical stress. So these over three factors in the end will decide our driving force. So therefore, our driving force, which will be equal to these three, and then overall, how large of this F will in the end to determine the mass flux of the atoms here. Of course, if you just pure look at this equation, sometimes not easy to understand, but as always, I think when we talk about the reliability, it's always remember that we are more focused on the use of physics to understand our mechanism, use of physics to describe everything, and then the equation just kind of like the backup to try to prove that the physics is really existing there. So also we can use simple physics to understand if you have the one interconnection line here, and as we already know, the first, once we have the electron flow in this interconnection line toward the left, so once we have the electron flow toward the left, and the first things will happen is our atom will be pushed toward the left as well. And this electron is mainly determined by the electric field. So you apply large electric field, for sure you have a large electron will push your atoms towards the left. So that's our first driving force. But the thing is not that simple. Once, after a certain while, we will start to foresee there's an accumulation of our atom on the one hand. So we start to see there is an atom, copper atom will be accumulate on the other side, on the left hand side. But the problem is there's always a fundamental equation, fundamental mechanism that the atoms, everything will try to move from the high concentration region to the low concentration region. That's what we call as a diffusion. So because right now we have a large concentration of the atom here, definitely diffusion will be happen. So we can start to expect the copper will try to diffuse back to the right. So this is our diffusion mechanism. So I think so far still pretty easy, can be understood, because that's all very basic. So either you have an electric field to push the atom to the left, and then once in the left side you have too many copper, and then therefore the concentration is high, then you will try to push back because due to diffusion. So the copper will try to diffuse to the right as well. So that's a second mechanism. That's what we call the concentration gradient. That will cause the diffusion. But the third one is because right now in this region we actually have the lots of the copper stay at this region. That will create what we call the compressive stress. Because you have to imagine this is not a single line. You have a line, you have a passivation, you have another line here. So once you create this here lock, for sure, if you look at this region, but your passivation is still there. So that will cause the passivation will induce a compressive stress back to your interconnection line. So we'll start to see we will have the third driving force. That's what we call the compressive stress. So that's the third one, mechanism. Of course, on the other hand, because the copper is moving to the left, and therefore we have a less copper in the right, so that's a depletion. And if depletion, actually we start to have a certain tensile stress. So that's a overall reason why the atom movements, if you look at the atom movement in the one interconnection line, that's overall issues that why we have the three different mechanisms in the end, try to find the balance and to reach to the certain status. So let me say again. So first of all, we apply the bias. For sure, once you apply bias, we have the electron flow electron flow will push the copper to the left. So that's the electric field drive the migration of the atom. So that's generally we call the electromigration. But once we have the copper atoms getting more and more in the one side, for sure, this high concentration will push the copper move back to the right. So that's due to the concentration gradient as well. And last one is mechanical stress. Because right now, if you consider this region with a nearby interpassivation, the nearby passivation will provide the compressive stress for this interconnection line. So that will be the third force. So now we will talk about one by one in details. The first driving force is electric field. So a movement of the metal ions in the electric field forced by the first one, direct actions of the electric field on the atoms. So that will induce the Coulomb force. So that's the same direction as the electric field. So that's here, right? Because that's a very typical Coulomb force that you apply the electric field and then the electron will be in the same direction of we apply the electric field. And the second one is what we call the momentum transfer. So the momentum transfer between the scattered electron and the atoms. So this phenomenon, this is these things. Because ideally, this is positive charge, and we apply the positive bias here. Ideally, the copper should not be flow toward the left, but now we see the copper will flow to the left because of this momentum transfer between the electron and atoms. And this is the phenomenon we call the electronic wave. So that's we call it electronic wave. And then this is in the opposite direction of the electrical field here. So now we know in the driving force one is mainly the combination between first and second. And unfortunately, the electronic wind is a dominant mechanism. So that's why we will see our copper atoms will move toward the left as well. So electron migration is due to the momentum transfer from the electrons moving in the Y, and this results the atomic migration towards the anode here. And this is some basic equation. The electrical force is equal to the charge, resistive, and most important is the current density. So that means as long as you have the large current density, you always have a strong driving force. And second one is a concentration gradient. So we already understand when there is a concentration difference between the one place compared to another place, the diffusions will always occur. So our diffusion force can be expressed by this times the concentration gradient. So that's a very basic equation. When everything we talk about diffusion, we always consider the same equation like here. And third part is the mechanical stress gradient. Gradient of mechanical stress acts as an external driving force for all-turn movement. So all-turn will prefer move from compressively stressed region to the region where in the tension stress. That's what we call the tensile stress region. So that means once we have the interconnection line, in the beginning, it's become like in this way. After a certain while, we start to see the accumulation on the one side, but also depletion on the other side. And the all-turns will prefer to move. And in the left-hand side, we have a compressive stress. And in the right-hand side, we have the tensile stress. So the all-turns in the end will prefer to move back in this direction. And this resulting coming from this stress gradient cause the backflow of the matter. So that will cause the backflow of this material. So then this is a equation. Here is our stress can be displayed in the equation as well. So that's the third mechanism. So in the end, the total mass flux. So the total mass flux can be combined these three components. The first one, concentration gradient. The third one, the driving force caused by the current density. And last one is mechanical stress. So the first term is describe the backflow of the all-turn due to build-up of the concentration gradient, and second term describing the driving force from electron beam, and then the third part is a term describe driving force from the mechanical stress gradient. So now I think so far, although in the beginning probably it's very difficult to understand why the all-turn will be moving in the one direction and accumulating somewhere. But I think with this explanation in the end, it's pretty simple. Just a matter with current density, matter with concentration gradient, matter with mechanical stress gradient. So far, I think all of the physics which we use try to understand this reliability are very general high school physics, nothing like the very complicated related to the quantum mechanics or whatever. But also, there is one issue that can further enhance this degradation is because of due to a flux divergence. So, if we only consider the movement of an all-turn alone, it's not sufficient to cause the values. On the other hand, flux divergence is necessary, leading to increase or decrease in all-turn concentration that will cause a depletion or accumulation of material at the flux divergence site. So imagine, as we already described in the beginning, if you look at your backend of line, it's not possible your interconnection line is always in the straight line. It's always possible to have this turning corner, and this turning corner will cause the flux divergence. So on the one side we have flux divergence, but on the other side we also have flux divergence as well. And the reason why the flux divergence will cause the certain issues can be also understood in this slide. So this is a schematic to show like the region of the example for the flux divergence. So if we look at this equation and consider in this case or this case, a divergence of a flux lead to imbalance in concentration and will result in, for example, if our current gradient J is smaller than 0, so that means your current is getting decreased. So this is a case of a gradient J smaller than 0. So that means because your current idea is 1, now it's become 0.5 here, 0.5 here. So your gradient J is negative because it's a current decrease, right? So if you have a gradient J smaller than 0, so that means your dc over dt is actually increased from this equation, right? This is negative, that means this is become positive. So once your dc over dt becomes positive, so dc over dt just means the concentration over time. So that means you have the mass accumulation, you have the mass build up. So that's why you have a heat lock formation. So this will leading to the compressive stress, and in the end to leading to the short between interconnection line. But why it will cause a short? This is because when you consider interconnection line, sometimes you have to be a little bit broad view, not only consider one line, because you have so many interconnection lines in the back end. So what you need to consider is, in the realistic case, we have the one copper line. On top of one copper, we have a one, that's we call the, so we have a many in copper line here. These are all our interconnection line. But in between, we have the passivation. Sometimes we just call it passivation, but sometimes we also call it interlayer dielectric. So, but basically, what the different wording means is almost the same. Just a certain insulator try to isolate the signal between these two metals. So we have the ILD in between. So imagine if you have the shear lock accumulation on the left hand side. So that means your interconnection line is not just look like in this way. It's actually, you start to see the shear lock formation. You have a shear lock formation. So your interconnection line is actually expanding the thickness because you try to have more alternate accumulation on this one region. But that's only the one case. That's only the case of a one single interconnection line. But now if you imagine these things is not only happen in this, but also happen in this region. So then what will be happen? You also have this. So now I hope you can understand why there will be the short happen, because this interconnection line is getting in touch with another interconnection line, because ideally we should have the ILD in between to isolate the signal. But unfortunately, because we have the accumulation of photons on this region, so this interconnection line is getting fatter, it's getting thicker. So this interconnection line is connected with another, and this one is connected with another. So that's why we start to see the short in this region. And once we have the interconnection line being short with each other, basically your chip is completely failed, because now you don't have very clearly signal. You cannot bias in the place you want. You cannot have a signal correct as you expected, because now everything just mess up with each other. On the other hand, if we consider the current gradient is larger, it's positive, that means this case. So right, because now you have a 1, 1, this become 2. So your current gradient is become positive here. And that means your concentration gradient is decreased. Concentration, not the concentration gradient, it's a concentration versus a time is decreased. So that means this is a certain mass depletion. We have a void formation. So that's why we have a void formation in this region. And this void formation clearly because your interconnection line is completely gone in this region. So you actually try to open one place to the another, so carrier cannot easily flow, and this causes the open. So that's in the end the impact of this interconnection reliability on our chip level signal or chip level performance, because on the one side you create a short with different interconnection line. On the other hand, you have the open, and that makes your interconnection line has a huge resistance. So the cause leading to the flux divergence can be several reasons. I would say nowadays, although this topic has been proposed since very early time, since these reliability issues has been already discussed for more than 30, 40 years, it's older than my age. But still, actually, the real mechanism or how to avoid these things still is under debate, because the problem is that our semiconductor technology is getting more and more complicated. So you have in the past, you only have a planar integration, so you have a less interconnection line divergence. But now we have the vertical integration, so we have very complicated flux divergence. So that will also drive this reliability issue. So this can be several possibilities: temperature, current density, mechanical stress, and also sometimes related to the materials, especially related to the interconnection material or the junction between the interconnection line and semiconductor. So therefore, the composition, contamination, grain size, grain orientation, and sometimes the barriers. The barriers is mainly related to your interconnection line, your metal line, and your semiconductor service. We always put some barrier here. That also will cause certain flux divergence. Okay, so let's still go back to the history that how people start to realize the electron migration is one of the critical semiconductor issues. As you can see, if you look at the history, this is a very, very old reliability issue, but nowadays still nobody can have great confidence to solve these issues. So this was already discovered by 1861, and from the 1950, so that's the first symmetry study by these two guys. The study is mainly focused on the correlation between the directional current flow and then the material transport. And the 60, this can be recognized as one of the main reasons for IC failure. So back to more than 60 years ago, we already realized that this electron migration is one of the main reasons that cause IC failures. And in 1967, there's a guy called J.R. Black. So he proposed a certain relationship between the NTTF, that's the mean time to failure, and also the current density and temperature. So that's what we call as a Black's law. So far, the Black's law is still quite true at this moment. We still use very often as a Black's law, try to estimate the failure time versus our current and temperature. And in 1975, there's a guy called Bleach. He discovered there's what we call the immortal wire. Immortal wire means that the wires can have the infinite lifetime. So you never see any failure in this interconnection line because of this what we call the Bleach length we will discuss. It's considered the product of current density and versus a wire length. That's what we call as bleach wire. Bleach length here. So the motivation to test the electron migration is that if we consider the normal working condition right now, nowadays, for the current density goes through in our interconnection line, it's around 1 to 3 MA per centimeter square. Probably you don't have a feeling how large it is, but if you compare the traditional electrical wire, so that's why we try to plug in, use our charger, whatever signal that you can see the black electrical wire. You can see the black electrical wire, the current density in the black electrical wire is so low compared to our current density in our interconnection line. So that's why this electron migration is getting serious. So you won't see this in the typical cable line because cable line current density is way too low. But in our chip, in our product, actually current density is very high. And now this is also another issues here. Decreasing of the line width. Why we have to decrease in the line width? It's the same as one of our roadmap to push the semiconductor for scaling. As I say, we are not only scaling the dielectric thickness, we're also scaling the interconnection line width. So now you can see, this is so I think everyone now should be very familiar. What does this mean? This is a time to failure at the 0.01%. And this is a condition that they use. It's a 1 mega amp per centimeter square here. So now you can see as the line width decrease, actually the lifetime is getting worse and worse. So the electron migration performance goes down with decreasing the line width, and also it goes down when we use some low K material here. So usually why we have to use a low K? Because we want to avoid the RC delay. So you probably know that in the interconnection line, we always have to consider the RC delay. RC delay is mainly considered resistance times the capacitance, and capacitance is related to our dielectric constant. So it will be always good we have a material that has a low capacitance. But that's also creates the issue of another reliability because our electron migration is getting poor if we have a low K material. Also, another issue is that if you follow the ITRS roadmap, So ITRS is an organization try to define the future roadmap for our semiconductor. So they will define roadmap for our gate, dielectric, our channel length, and so on, so on. They also will define the pitch or interconnection line width. So now you see, if we consider the 32 nanometer technology down to 7 nanometer technology, of course we reduce the pitch, but also our contact area is reduced. But the contact area is reduced, the line width also reduced, and therefore this will cause the huge increase of our current density. So the current density is dramatically increased. So, and then if you look back for the previous equation, we will talk about the issue related to electron migration. You will definitely figure out that the current density is one of the key factors. So as long as you have a high current density, you always got a problem for our electron migration. And this is the things happening for 7 nanometer, but now we are on the edge of the 2 or 3 nanometer, even down to 1 nanometer. So we can foresee the current density is getting crazily increased. So the required Jmax increase dramatically when scaling to the lower dimension. So this is also, once our scaling is happening, our current density is higher, and that means this is a case with a higher current density, with a regular current density, and we found out that if we test at 3 mega amp per centimeter square, our lifetime is highly decreased. So there's a significant decrease in the electron migration performance when increasing our current here. So this is what we already discussed for the electron migration. So the electron migration is basically considered as a mass transport of a metal ion for conductor induced by the flow of the electrical charge carrier through that conductor. This driving force is known as electron wind force, and this results from the momentum exchange between the electron and diffuse metal ions here. So I think so far, if you pay attention to our beginning explanation, I think this slide is pretty easy for everyone, because just illustrate the concept again, we use another schematic. So depletion and accumulation will happen at the flux divergence region, for example, here and here. So the cause for this electron migration is basically due to the momentum exchange with electrons here, and this will in the end lead to the, for example, we will form the void, and void will open circuit, and here lock will short between lines or layers, and always the temperature and current density is an acceleration factor. So because of the high temperature push the driving force larger, of course the current density is always another acceleration factor. And there are so many influence factors, I would say so far still all this is under discussion, because each time if we try to employ the new material for interconnection line, and that will completely change all of our understanding, because different material has a different relation for temperature, different grain size, and also different diffusion, however. So these all will cause influence on our electron migration. And some of the prevention as shown here, first one, for example, design rule, if you can enlarge the pitch, or you can avoid the region that can cause the heel lock, that probably you can save your interconnection line without influence from the electron migration or new material to slow down the interface diffusion. So that's why if you really work on the interconnection line, you will start to need to explore the very complicated material like shown here. I'm not the expert in this material, but as far as I know, this is all related to material science, chemistry, because you can see this is another typical one element material. This is a compound element, but the purpose is try to avoid the electron migration. And sometimes we also need to have this, for example, alloy interconnection line. So that's why if you look at the industry, if you happen to know the interconnection line, the material in the industry level interconnection line, you probably will, in the beginning, will be confused why they don't use a pure aluminum, they don't use a pure copper, they use this very complicated alloy. And most of the reason is because they want to improve the electron migration. They want to avoid these reliability issues. So next time if you see the aluminum copper, please don't be surprised, because this is just a purpose to try to avoid the electron migration. In reality, aluminum is definitely one of the most often used metal that can be used in interconnection line, and copper as well. But in reality, it's getting more often. You will see, even in the TSI, if you look at the TSI process, when they deposit aluminum, it's not the pure aluminum. It's actually the aluminum, copper, but just only 2% copper. And the reason why we have to put the 2% copper in the aluminum, this is because try to improve the electron migration reliability. So nowadays it's getting, for the university for sure, we still mainly use aluminum because that's for the easy process, and also it's cheaper, and there's no much like the equipment requirement. But in the industry, it's very seldom, it's very not often to use the pure aluminum. It's mainly use aluminum copper, but also the copper is not 50%, it's only 2%, because that's for the purpose to improve the interconnection reliability. So here is some experimental result. We can see on the one side, left hand side, we see the open. This is because of due to the void. And on the one side, we have this short. This heel lock formation will cause a short between the line to line. And this is some real-time image that how the void growing, moving, and leading to the failures here. So now you can see this time with the 63 hours, we start to see the void growing. And as long as the time increase, we start to see it's completely open. Okay, so we will take a break for 10 minutes. We'll come back in 10 minutes later. 对，走。可是这上面有写，帮我改成那个电子书。这个。对。而且我先带去。对，你再帮我用另外。
就是我看考古，我的结论是，你看那个video里面就这样，感觉应该90%的东西会这样子，有的时候都是有点抽象。好像我可以在因为我看考古里面，可以在我怎样那个东西，有看到可以在我个词上面这里有看到。有。啊，有吗？有。CBD 那个也是。
那你准备好了吗？
啊？
你准备好了吗？今天是考试的。
基本上是准备好了。
应该是4点。对，4点到4点半，他们会收卷了。
收卷？原来是考场。原来是考场。有考场吗？
那我们是线上考试吗？
对啊。所以我们不是线上人士。
我记得是我朋友是以前他考过了，所以他跟我说是没有是那么多压力的，轻轻松松的。
因为应该我们25题吧？看到我们是25题，我们30分钟可以。
25题吗？
是吗？还是40题？我不懂。
我觉得我不要担心啊。
有这种情况，我们看是那个考古，然后我们看到很精彩。对，而且他有是那种看这个赛，就是我看赛，这个感觉很重要的东西。
对。那我觉得半导体元件的是印度的教授的课程，你会
这过，反正我成绩也不管成绩，我只是可能会过，我只是不要遇到不能过，然后过了那个字在那边要重考。因为我教授是说基本上都能过的。
对。
我还是要过完，不管怎样子。但哪怕我这个学期我上个学期还修了一个4，那个如果说我不要修4，不要修，4我就不敢给你4了，我上这个4我有点怕了，算了，可能。那么就
你还在上那堂课还是比较快？
应该是有这个，反正只要能把手续做好，对我而言，主要就是目的因为毕竟你是哪路科的吗？你是那个美光的那个助手是吗？对，你们是去哪路科？我去哪大学？对我而言，一定要是4+4的，因为我有这。就下面都是。
对对对，追剧系统现在可能，你那个可不可以？我们过来拿这个，它这是还是？ Okay, so then we will continue. And the next one I would like to introduce is this bleach experiment. And also, there's some series that he proposed nowadays, still very interesting and useful for us. So this experiment was proposed by Bleach in the 1975 to try to measure the drift velocity, especially related to the mass transport drift velocity. And so he proposed this experiment. So this is an experiment considered under the constant current force through the gold layer on top of a certain metal track layer. So the idea is we force the current on the left hand side and we try to monitor the gold, this is gold, the movement of the gold. The movement of a gold. So under influence of the electron wind, we will start to see the gold will move. This will result in the depletion at the cathode. So that means this will depletion at this region. And also accumulation on the other side here. So that's the experimental result here. We can see there's an accumulation on the gold stripe layer on the other side. This experiment is very simple. The idea is simple. We just force the current through the bottom metal layer and we try to observe the gold layer on top and to see this gold will shift or not. So it's a very clearly evident to see that it's indeed the atoms will be movement due to the electron, due to the current. And afterwards, he started to get in more and more detailed study. So in this case, in this graph, it's showing like the drift velocity in the y-axis versus the current density. So basically, we can see the velocity is certain proportional to our current density as well. So this Bleach experiment allows to measure directly the dependency of atom drift velocity on the current density and temperature. So that's a thing. So we can use this way to estimate how the drift velocity for this mass transport, for in this case, is using as a gold atom movement. So the beach line, but now afterwards, actually, this guy also found out that another very interesting result is that for line below the critical length, there's no migration is observed. So we won't see any migration. And this is mainly because of the balance of the backflow atoms. And in the end, the driving force is completely disappear. So as we already know, when we consider the driving force of electron migration, we can see this schematic. We have an electron wind try to push the atom to the left. And also once the atoms accumulate here, we have the gradient. We'll try to push, no matter for stress gradient or concentration gradient, will push the atom flow to the right as well. So there's a balance. If the length is shorter enough, that these two forces can be balanced with each other. So that means once we have a length below the critical length. Once we have a line below this critical length, and actually we will have the very good balance between these two mechanisms. In the end, there's no degradation will happen. So you can look at this experimental result. This is a case with a 100 micrometer. And also, this is a case for 30 micrometer. So now we can see, we should consider as a length of the 30 micrometer. Basically, we won't see any obvious resistance increase. So that means, in this case, we won't see any degradation. So that's good for this reliability study, because in the end, we won't see any degradations happen. So when we consider the bleach length, the first one is the mechanical stress. So as we already know, the gradient of a mechanical stress acts as an external driving force for the atom movement. So the atom will prefer move from the compressive stress region and accumulate the location in the tensile region. So that's we already know. That's why that we will see this bleach length, because in the end there's a strong backflow of this matter, of this material, due to the stress gradients. And so that's why we see the vacancy will move in the right hand side, and this will result in the stress gradient cause the backflow of the matter, and that can be illustrated by the equation below. And so in this case, we can also use a very simple equation to estimate what will be the critical length that can cause this balance between these two mechanisms. So we just put these two equations equal to each other. The left hand side is the driving force caused by the wind force, and right hand side is the driving force caused by the stress gradient, and then the bleach length can be happen as long as this equation is equal to each other. So it is so-called bleach length, LC. And the critical product for this can be divided by here. So that means there's always a product between the LC times the current. So this gives us a way to estimate the bleach length here. So that means if the shorter stripe length, the larger the current density required to have the electron transfer. For fixed current density, if a conductor length is shorter than the corresponding bleach length, the line will never fail. So that's another interesting conclusion, but this is only limited in the length where it has a relatively short length. But in reality now, we consider our backend of line, our interconnection length right now is a pretty long length at this moment. So this is some of the paper reported. You can see it's interesting to see this guy who proposed this theory is 1975. So that's way too longer before. I was not even born at that moment. But if you look at the paper reported, the data nowadays, this is not the latest result. This is already more than 10 years ago. This is a paper published in 2008. But also, one thing reminder, this is paper published by TSMC. So this showing the two results here. One is the mechanism has been already exploding a long time ago, but nowadays we're still suffering this issue. That's why there's still paper talking about this, right? Another is it would be interesting to let you know that what we learn from reliability, no matter for electron migration, TDB, BTI, or later ESD, if you start to work on your presentation, start to look on the literature, I would say what we learn is pretty practical concern. It's pretty like not the knowledge is just only for theoretical understanding. It's pretty like the industry level challenge. It's an industry level issues. That's why after so many years, TSMC people still try to understand what will be the bridge length in their technology. Of course, now we are in 2024, so it's already 60 years beyond this 2008. I believe you can still find lots of literature talk about bridge length, because nowadays we have a different current density, we have a different material, we have a different VR, we have vertical integration. So now this issue is always come again. So this is a paper published by the TSMC, and they try to compare it of the experiment data with the simulation, but the simulation they use is based on Monte Carlo simulation and experimental data in their technology. So you can see this is a channel length, this is the length for 50 micrometer. So in the case of 50 micrometer, actually it's pretty close to their bleach length, the critical length for bleach length. So that's why they have very good lifetime and with only 5% failure probability. But in the case of this one, for example, 250 micrometer. So that means we have a huge failure reliability. That also gives us a sense that if you consider the 3D integration, if we want to always avoid the back-end reliability, we need to thinner our passivation, or even the thinner the substrate thickness. So this is, for example, we have a chip 1, we have chip 2, we have a chip 3. So how could we leverage the understanding of the bridge length to improve the reliability? That means we need to make this shorter as possible as we can. If we can make this, if back to the TSMC paper published in 2008, they say the 50 micrometer can give us a great lifetime. So that means we should make this TSV smaller than 50 micrometer. Of course, that brings some other challenges. For example, our chip substrate thickness should be below 50 micrometer. That's a little bit complicated, but at least this gives a hint how we can use, how we can leverage some theoretical understanding to in the end to implement our overall reliability. Also for here, if we can make this below 50 micrometer, we can save for our chip without suffering this electron migration reliability. I think that's the goal why we have to understand this critical length, because in the end, as I say, the purpose for reliability is not only understanding investigation. In the end, we want to propose a strategy to improve the device reliability. We want to propose a strategy to enhance our chip, our product robustness. Okay, so here is a short summary for our electron migration. So that's a course. It's basically just some wrap up what we have been discussed. So it's mainly related to the momentum exchange with the conduction electron. So that will cause a void. We have an open circuit here, locks, and so on, and even have the short between line to line. I think this is very similar to what we have been discussed. And also, one of another things is that the electron migration start become important when our current density is larger than 10 to 6 amp per centimeter square, and therefore, it's also everyone should be aware of that. As long as we have the power metal in the IC, in all kinds of technology. Whatever you are working on, you are working in the power device, logic device, package level, whatever memory, we always suffer this electron migration in the interconnect, context, and vias. Okay, so that's also another experimental result to show that we have the void formations here. We have a here lock at this region. And here is the result we have been shown. Okay, so as we already say in the schedule that we will let you have the time to discuss with your team members. So in next week we have the TDDB presentation. So we will stop at this moment, and you can feel free to discuss. If you find it difficult to meet your team members for any kind of excuse, I think it's a good moment to meet at this moment. Okay, so by the way, we have some grading homework here, so you can please pick up to check your grading homework. And if you will have any question, you can check with our TA at this moment, because they are the main person who helped me to grading the homework. So you can check with them to understand why you didn't get the full score if you missed some questions. So see you guys next week.